This lecture is of software architecture. It is about modifiability. This is your professor Atif Reed Muhammad. Modifiability in architecture refers to the ease with which a system can be changed to accommodate new requirements, fix defects, or adapt to evolving technologies. It is a key quality attribute that influences the long term maintainability and scalability of software. A modifiable architecture typically employs design principles such as modularity, loose coupling, and separation of concerns, permitting changes to the localized without extensive ripple effects. Techniques like abstraction, encapsulation, and the use of well defined interface or interfaces further enhance modifiability by isolating components and reducing dependencies. To achieve high modifiability, architects often adopt patterns like microservices, layered architectures, or plugins based designs, which enable incremental updates with minimal disruption. In this chapter, we'll discuss what is modifiability. I just started discussing with you the modifiability general scenario, tactics for modifiability, a design checklist for modifiability, and then we'll go from there. So, as mentioned earlier, modifiability is about change, and our interest in it is in the cost and risking of making changes. To plan for modifiability, an architect has to consider three questions: what can change, what is the likelihood of the change, when is the change made, and who makes it. So let me reword my earlier modifiability introduction. To achieve high modifiability, architects often adopt patterns like microservices, layered architectures, or plugin based designs, which enable incremental updates with minimal disruptions. Documentation, clear coding, standards, and automated testing also play a crucial role in ensuring that modifications can be made efficiently and safely. By prioritizing modifiability, organizations can reduce technical debt, accelerate feature delivery, and respond more effectively to changing business needs, ultimately extending the lifespan and value of the software system. Modifiability general scenario. So this is right in front of you, that has the portion of scenario is source, stimulus, artifacts, environment, response, response measures. So the possible values can be for source: end user, developer, system administrator. Stimulus is a directive to add, delete, modify functionality, or change a quality, attribute, capacity, or technology. Artifacts are code, data, interfaces, components, resources, configurations, and the list can go on. Environment is runtime, compile time, build time, initiation time, design time. Response, one or more of the following: make modifications, test modification, deploy modification. Response measure, cost in terms of number, size, complexity of affected artifacts, efforts, calendar time, money, direct outlay, or opportunity cost. Extent to which this modification affects other functions or quality attributes. New defects introduced. So let's look into this with an example. A university management system, UMS, is a complex software platform that handles student enrollment, course scheduling, faculty management, and financial operations. Modifiability is crucial in this system because universities frequently update policies, introduce new programs, and adjust administrative workflows. For instance, if the university decides to implement a new grading system or add an online learning module, the architecture should allow these changes without requiring a complete system overhaul. A well designed UMS or university management system would use modular components such as separate services or for admissions, academics, and finance, so that updates to one module do not disrupt others. Consider a scenario where the university introduces a new scholarship program requiring integration with both the admissions and financial aid modules. A modifiable architecture would allow developers to extend the financial aid component without rewriting the entire admissions process by using well-defined APIs and service-oriented architecture or SOA. The new scholarship logic can be plugged in seamlessly. Additionally, if the system follows the open-closed principles, open for extension and closed for modification, existing functionalities remain stable while new features are added. This reduces regression risks and speeds up deployment. Another example is adapting a regulatory changes such as a new data privacy laws requiring updated student record storage. A modifiable UMS would isolate the data access layer, permitting compliance updates such as encryption or anonymization without altering business logic. If the system is used a layered architecture with clear separation between presentation, business logic, and data storage, modifications can be confined to the affected layer. Furthermore, if the system employs configuration files or feature flags, administrators could toggle new privacy rules without code changes, enhancing agility. So hopefully this has given you some understanding. Sample concrete modifiability scenario, as we are looking at the UMS, the developer wishes to change the user interface by modifying the code at design time. The modifications are made with no side effects within 3 hours. So if I continue the example that I shared with you, scalability is another aspect where modifiability proves beneficial. Suppose a university expands to offer hybrid online plus in-person courses, necessitating real-time attendance tracking. A rigid system might struggle to integrate third-party video conferencing APIs, whereas a modifiable one would allow such extensions via plugin architectures or middleware by designing the attendance modules with interfaces rather than hard-coded dependencies. New tracking methods such as biometrics or LMS integration can be added with minimal rework. Automated testing and CI/CD principles further ensure that modifications do not introduce instability. Goal of modifiability tactics. Tactics to control modifiability have their goals controlling controlling the complexity of making changes as well as the time and cost to make changes. So ultimately, a modifiable university system reduces maintenance costs, improves adaptability, and extends the software's lifespan. Whether accommodating new academic policies, integrating emerging technologies, or complying with legal changes, a well-architected UMS ensures that modifications are efficient and low risk. By leveraging design patterns like microservices, dependency injection, and domain-driven design, universities can future-proof their systems while maintaining operational continuity. This flexibility is critical in an environment where administrative and academic requirements evolve continuously. So let's look into the goal of modifiability tactics with the same example that I just shared with you. The primary goal of modifiability tactics in a university management system is to minimize the cost, time, and risk associated with changes while ensuring system stability. Universities operate in dynamic environments where academic policies, regulatory requirements, and technological advancements frequently evolve. A well-architected UMS must anticipate these changes by employing tactics such as modular decomposition, loose coupling, and encapsulation. For example, separating the student enrollment module from the financial billing module ensures that the change in fee structures, such as introducing installment payments, does not require modifications to unrelated components like course registration. By reducing interdependencies, these tactics localize changes, preventing cascading failure and simplifying maintenance. Another key objective is enhancing flexibility through abstraction and interfaces. So the change arrives, the tactics to control modifiability, changes made, tested and deployed within the time and budget. So let's continue that learning with the UMS. Another key objective here is enhancing flexibility through abstraction and interfaces. A UMS often needs to integrate with a third-party system such as learning management systems or LMS, payment gateways, and government accreditation portals. Instead of hard coding these integrations, modifiability tactics like the dependency inversion principle or DIP and adapter patterns allow the system to swap external services with minimal rework. For instance, if the university switches from one LMS, such as Moodle, to another, such as Canvas, a well-defined interface for course synchronization offers that only the adapter implementation needs updating, not the entire academic module. The approach future-proofs the system against vendor lock-in and technological obsolescence. So the tactics are given here, and you can look into that in detail. However, the modifiability tactics aim to simplify testing and deployment of changes. Our universities cannot afford systems downtime during critical periods like admissions or exams. Techniques such as feature toggles, version APIs, and incremental rollouts allow updates to be deployed safely with minimal disruption. For example, if a new grading policy is introduced, it can first be released to a small group of faculty and for testing before the full rollout. Additionally, automated regression testing and CI/CD pipelines ensure that modifications do not break existing functionality. By prioritizing these tactics, a UMS remains agile, scalable, and resilient, capable of adapting to both anticipated and unforeseen changes without compromising operational efficiency. Hopefully this example has helped you. Let's go and look at reduced size of a module. Split a module. If the module being modified includes a great deal of capability, the modification costs will likely be high. Refining the module into several small modules should reduce the average cost of the future changes. So now let's look into this within the UMS or University Management System. To enhance modifiability, a UMS should decompose large modules into smaller, more focused components. For example, instead of monolithic student management module, the system could separate functionalities like enrollment, attendance, and academic records into independent microservices or submodules. This reduces complexity, making each component easier to understand, test, and modify without affecting unrelated features. Smaller modules are also allow development teams to work in parallel, escalating updates while minimizing merge conflicts. Smaller modules improve maintainability by enforcing single responsibility principles. Each component handles one specific task, fee calculation, or course scheduling. This granularity ensures that the changes such as adjusting a grading algorithm or adding a new payment method are confined to a single module. Additionally, smaller modules simplify debugging and performance optimization as issues can be isolated and resolved faster. Techniques like domain driven design (DDD) helps logically partition modules based on business capabilities such as admissions versus examinations. Adapting microservices or modular monoliths allows a university management system to scale and evolve efficiently. For instance, the examination module could be split into paper submission, grading, and result publishing services, each with its own database, schema, and API contracts. Using event driven architecture further decouples modules such as student registration and event triggers, updates in attendance, and billing without direct dependencies. This approach ensures that even as the university introduces new processes, hybrid exams, changes remain localized and low risk. By prioritizing small, cohesive modules, a UMS achieve greater agility, easier compliance updates, and long-term sustainability. Increase cohesion. Let's look into this with an example. If the responsibilities A and B in the module do not serve the same purpose, they should be placed in different modules. This may involve creating a new module, or it may involve moving a responsibility to an existing model or a module. Let's look into this in the UMS. To improve maintainability and reduce complexity, a UMS should enhance and ensure that each module has high functional cohesion, meaning its components are tightly related to a single purpose. For example, a course management module should exclusively handle course related operations, creation, scheduling, prerequisites, rather than mixing in unrelated tasks like faculty, payroll, or student housing. By grouping only relevant functions together, the system becomes more intuitive, easier to modify, and less prone to unintended side effects during updates. Highly cohesive module minimize unnecessary dependencies and streamline development. For instance, an exam processing module focused solely on exam scheduling, grading, and result publishing, rather than also managing classroom bookings, reduce the risk of changes in one area breaking another. This clarity also simplifies testing since each module has a well defined scope. Unit tests can verify behavior more precisely. Additionally, high cohesion aligns with domain driven design (DDD), where the module map to real world university processes such as admissions, financial aid, making the system easier to understand for both developers and stakeholders. To enforce cohesion, architects can apply single responsibility principle or SRP, such as split a bloated student services module into distinct modules for registration, academic advising, and degree audits. Use bounded contexts from DDD to define clear ownership, such as library management module handles only books, loans, fines, inventory without overlapping the course materials. Leverage modular design patterns such as microservices or layered architecture to physically separate cohesive units such as tuition calculations, service independent, or scholarship processing. By prioritizing cohesion, a UMS becomes more modular, scalable, and adaptable to changing university needs while reducing technical debt. Now let's look into reducing coupling. A well designed UMS should minimize dependencies between modules to improve maintainability and flexibility. For example, the student enrollment module should directly depend on the billing system. Instead, they should communicate through standardized interfaces or events. This loose coupling ensures that changes to one module, like modifying payment rules, won't require modifications to unrelated components. Techniques like dependency injection and interface segregation to help achieve this by removing hard-coded dependencies between components. Reduced coupling make the system more resilient to changes and easier to scale. When the course scheduling module does not directly depend on the faculty management system, universities can update one system without fear of breaking the other. Replace individual components like switching to a new learning management system with minimal impact. Scale high demand services like exam processing independently. This isolation also simplifies debugging since issues can be traced to specific modules rather than complex interaction patterns. Implementation strategies for loose coupling. Key approaches include event driven architecture. Modules communicate through events such as student registered, event triggers, processes in other system. API gateways provide controlled access between services with clear contracts. Domain boundaries enforce strict separation between different business domains, admissions versus academics versus finance. Adapt pattern or adapter pattern. Use intermediate or intermediaries to connect to external systems like government accreditation portals. By systematically reducing coupling, a UMS becomes more adaptable to policy changes, new regulations, and evolving educational technologies while maintaining system stability. So, again, I have discussed the restrict dependencies, refactor, abstract common services. Here, restrict dependencies can restrict the modules which a given module interacts with the dependents on. Refactor is undertaken when two modules are affected by the same change because they are at least partial duplicates of each other. Abstract common services, other where two modules provide not quite the same but similar services. It may be cost effective to implement the services just once in a more general abstract form. Defer binding. In general, later in the life cycle, we can bind values the better if we design artifacts with built in flexibility. Then exercising that flexibility is usually cheaper than hand coding or a specific change. However, putting mechanisms in place to facilitate that late binding tends to be more expensive. Let's look into this with an example. Deferring binding refers to delaying implementation decisions until runtime or configuration time, rather than hard coding them during development in a university management system. This approach enables greater flexibility when policies or processes change. For example, instead of hard coding grading scale A to F in the exam processing module, the system could load them from a configuration file or a database. This allows administrators to modify grade boundaries or introduce new grading systems like pass or fail without requiring code changes or redeployment. Similarly, business rules like enrollment deadlines or tuition calculations formulas can be externalized as configurable parameters rather than being embedded in the application logic. By deferring binding, universities gain the agility to adapt to changing requirements without technical intervention. Key advantages include policy flexibility, multi-tenancy support, easier compliance. And for to learn more about policy flexibility, academic policies like attendance requirements or credit transfer rules can be updated through configuration rather than code changes. In multi-tenancy support, different departments or campuses can operate with customized rules while sharing the same code base. Easier compliances, regulatory changes like data retention policies can be implemented by updating configurations rather than modifying core systems. This approach also reduces the deployment risks, or critical business rules can be modified without touching the underlying application code. Implementation strategies for deferred binding. Effective techniques for deferring bindings in the university management systems include externalized configuration, where we store business rules in a database, JSON, XML files, or environment variables. The next is rule engine or rules engine or rules engines. Use tools like Drool to manage complex, changeable business logic separately from application code. Plugin architecture allow modules like payment processors or LMS integrations to be loaded dynamically at runtime. Feature flags Enable disable functionality through configuration to support A/B testing or phased rollouts. By systematically applying deferring binding, a UMS becomes more adaptable to institutional changes while maintaining system stability and reducing maintenance overhead. Runtime customization options empower administrators while keeping the core system robust and maintainable. Now let's look into design checklist for modifiability. Design checklist for modifiability. Application needs allocation of responsibilities. Application can be university management system. Determine which changes or categories of changes are likely to occur through consideration of changes in technical, legal, social, business, and customer forces. For each potential change or category of changes, determine the responsibilities that would need to be added, modified, or deleted to make the change. Determine whether uh, what other responsibilities are impacted by the change. Determine an allocation of responsibilities to modules that places as much as possible responsibilities that will be changed or impacted by the change together in the same module and places responsibilities that will be changed at different times in separate modules. Coordination model. The determination or determine which functionality or quality attributes can change at runtime and how this affects coordination. For example, will the information being communicated changes at runtime, or will the communication protocol change at runtime? If so, ensure that such changes affect a small number of set modules. Determine which devices, protocols, and communication paths used for coordination are likely to change. For those devices, protocols, and communication paths, ensure that the impact of changes will be limited to a small set of modules. For those elements of which modifiability is a concern, use a coordination module or a model that reduces coupling such as publish, subscribe, differs, binding such as enterprise service bus, or restricts and dependencies such as broadcast. Data model determines which changes or categories of changes to the data abstractions, their operations, or their properties are likely to occur. Also determine which changes or categories of changes to these data abstractions will involve their creation, initialization, persistence, manipulation, translation, or destruction. For each change or category of change, determine if the changes will be made by an end user, system administrator, or developer. For those changes made by an end user or administrator, ensure that necessary attributes are visible to the user and that the user has the correct privileges to modify the data, its operations, or its properties. For each potential change or category of change, determine which data abstractions need to be added, modified, or deleted. Determine whether there would be any change to the creation, initialization, persistence, manipulation, translation, or destruction of this data abstraction. Determine which other data abstractions are impacted by the change. For these additional abstractions, determine whether the impact would be on their operations, properties, creation, initialization, persistence, manipulation, translation, or destruction. Ensure an allocation of data abstraction that minimizes the number and severity of modifications to the abstraction by potential changes. The design your data model so that the items allocated to each element of the data model are likely to change together. Mapping among the architectural elements, determining if they're desirable to change the way in which functionality is mapped to computational elements such as processes, threads, processors at runtime, compile time, design time, or build time. Determine the extent of modifications necessary to accommodate the addition, deletion, or modification of a function or a quality attribute. This might involve determination of, for example, execution dependencies, assignments of data to a database, assignments of runtime elements to process threads or processors. Ensure that each changes are performed with mechanisms that utilize deferred binding of mapping decisions. Resource management. Determine how the addition, deletion, or modification of a responsibility or quality attribute will affect resource usage. This involves, for example, determining what changes might introduce new resources or remove old ones, or affect existing resource usage. Determining what resource limits will change and how. Ensure that the resources after the modification are sufficient to meet the system requirements. Encapsulates all resource managers and ensure that the policies implemented by those resource managers utilize are themselves encapsulated and binding are deferred to extent possible. Binding time for each change or category of change. Determine the latest time at which the change will need to be made. Choose a defer binding mechanism as mentioned earlier that delivers the appropriate capability at the time chosen. Determine the cost of introducing a mechanism, the mechanism and the cost of making changes using the chosen mechanism. Do not introduce so many binding choices that change is impeded because the dependencies among the choices are complex and unknown. Choice of technology. Determine the modifications are made easier or harder. So I suggest you look into this at your convenience. And now let's summarize. The modifiability deals with the changes and the cost of the time or money of making a change, including the extent to which this modification affects other functions or quality attributes. Tactics to reduce the cost of making a change include making modules smaller, increasing cohesion, and reducing coupling. Deferring will also reduce the cost of making change. Hopefully this has given you some understanding in depth. See you in the next lecture. Happy learning.